Welcome back, ladies and gentlemen. Today, we will be performing and explaining a salt bridge and galvanic cell lab. Ready? Let's start filling our solutions. On the left, we'll have copper 2 sulfate, or CuSO4. For our second solution, we're going to have zinc sulfate, or ZnSO4. Since we are constructing 2 electrodes, let's add solid copper to the copper sulfate solution. To finish constructing our zinc electrode, let's add solid zinc to the ZnSO4 solution. This is a voltmeter. We'll be using this to measure the voltage of our galvanic cell. It has 2 wires, a red one and a black one, which we will be clipping to the copper and the zinc solid. Looking back to the beakers, we're going to add the red clip to the copper solid and the black clip to the zinc solid. Now we've added our salt bridge. We'll circle back to this one later. Now, let's set a timer for 30 minutes to let our solution marinate, and this will give us a more accurate reading of the voltage for our galvanic cell. While we wait, do you think the copper electrode will be the anode or the cathode of the cell? If you said anode, you'd be correct! Good job! The reaction for this solution will be aqueous Cu2 plus 2 electrons yields solid copper. Let's take a look at our zinc electrode. If the copper electrode was the anode, what do you think the zinc electrode will be? If you said cathode, that's correct! The reaction for the zinc electrode will be Zn2 plus aqueous plus 2 electrons yields solid zinc. Now, let's circle back to our salt bridge. Let's take a look at our enlarged salt bridge. In the salt bridge, we have a solution of sodium sulfate. Let's take a look at our visual. This circle is representing our Na plus cation. In a salt bridge, the cation will move towards the cathode because it's reducing or gaining electrons. The cation will move towards the cathode because it will attract the positive cation due to the cathode being negatively charged. Likewise, NO3- or nitrate will move towards the anode. This is because the anode is losing electrons that are flowing through the wire towards the cathode. Since the anode is positively charged, the anion will be attracted to it. Alright everyone, our 30 minutes is up. Before we look back at our cell, let's hypothesize what we think the cell voltage will be. Let's take a look at our reactions and their voltages. First, let's look at the half-cell reactions of copper and zinc. Next, we have the E-cell voltages. For zinc, it's going to be negative 0.76, and for copper, it's going to be positive 0.34. When calculating the E-cell of a galvanic cell, you must flip the sign and half-cell reaction with the most negative standard reduction potential. It is important to note that this will also be the anode. In this case, it would be zinc. Since all galvanic cells are thermodynamically favorable, we can look at the equation delta G equals negative NFE. Since delta G must be negative to represent a thermodynamically favorable cell, the value of E cell must be positive in order to create a negative product. This means that we can predict that the cell voltage of our cell will be positive.